Well, hello, ladies and gents. Hope you're doing well today. So, what I would like to do now is walk through the explanation for the water potential practice problems. Uh, when I tried writing on the screen, it was sort of difficult to write legibly. So, to work through all these practice problems, what I decided to do was just write it out on a piece of paper, snap pictures of it, and then sort of walk you through this. So, I know it's sort of suboptimal to not be able to write and talk at the same time, but I appreciate your patience with this. So let's look at the first problem here. It says if a cell's pressure potential is 3 bars and its solute potential is negative 4.5 bars, what's the resulting water potential? Well, let me toggle back here. So we know that water potential is pressure potential plus solute potential. So if we have a pressure potential of 3 and a solute potential of negative 4.5, then the overall water potential ends up being negative 1.5 bars. The second problem here, it says the cell from question 1 is placed in a beaker of sugar water with a solute potential of negative 4 bars. In which direction will the net flow of water be? So again, water will flow in and out of the cells, but they're looking at sort of the overall flow of water here. So I like to sort of draw or write down what we know. We know inside the cell it's going to have a water potential of negative 1.5 bars. If we look at the beaker, the pressure potential in an open container will be zero, so the pressure potential is zero. So then we need to figure out what the solute potential is, and they said the solute potential is negative 4 bars. So the water potential for the beaker is going to end up being negative 4 bars. So if we draw that in here, it's negative 4 bars in the beaker, negative 1.5 bars inside the cell. And since water flows from high water potential to low water potential, there's going to be a net flow of water out of the cell. Alrighty. Question 3. The original cell from question 1, the one with negative 1.5 bars, is placed in a beaker of sugar water with a solute potential of negative 0.15 megapascals. We know that 1 megapascal is 10 bars. In what direction will the net flow of water be? Well, again, if we look at this, we know the water potential in that original cell is negative 1.5 bars. If we go to calculate the water potential in that second beaker, again, it's an open container, so the pressure potential remains at 0 bars. And then what we'll just do is convert the 0.15 megapascals to bars, so it's a 10 to 1 ratio there. So it ends up being 1.5 bars. So if the pressure potential is 0 and the solute potential is negative 1.5 bars, then the water potential in that second beaker is 1.5 bars. And since the water potential inside and outside the cells is equal, it's an isotonic solution, so there's going to be no net flow of water. Water, again, will flow in and out of the cell, but it'll just do so at the same rate. So that's the first few problems. Let me bounce back here and grab stuff for this. Oops, sorry, that's not what I'm wanting. Um, there we go. Again, I appreciate your patience as I sort of fuddle my way through this. Okay, if we look at problem 4, the value for water potential in root tissue is negative 3.3 bars. You take that root tissue and you place it in a 0.1 molar solution of sucrose at 20 degrees Celsius in an open beaker. What's the water potential of the solution, and which direction is water going to flow? Well, we know quite a bit here, right? We got the molar concentration, it's 0.1 molar. It's sucrose, so since it's a carb like that, it'll form rings in solution, so it'll be uh, uh, ionization constant of 1, so it'll just be in one piece. And they gave us temperature in Celsius, so we just have to remember to convert it to Kelvin. And they gave us that final clue that it's in an open beaker. And again, if it's an open beaker, the pressure potential will be 0. So again, quite a few clues given to start this off. So again, we want to know what the water potential of the beaker will be because they gave us the water potential for the cell. So if we go to calculate the water potential for the beaker, again, it's in an open container, so the pressure potential is 0. The solute, to calculate the solute potential, remember, it's an ionization constant of 1. Since it's a carb, it'll form a ring. We jot down the concentration, which is 0.1 molar. Here is that constant, the 0.0831. And, excuse me, We take the temperature of 20 degrees Celsius, add it to 273 to convert to Kelvin, and we wind up calculating a water potential for the beaker of negative 2.43 bars. So it's 2.43 bars in the beaker minus, or negative 2.43 bars in the beaker minus 3.3 bars in the cell. And since water flows from high to low potential, you're going to have a net flow of water into the cell. Okay. Now, in the second part of this, they give you a for instance. Here they're saying rather than sucrose, what if you use sodium chloride? So sodium chloride will dissolve into two particles in solution. So everything else is the same, right? It's 0.1 molar. Um, yeah, and everything else is the same. So all we're doing with this in the second part of it, you set everything else up the same. It's still an open beaker, so the pressure potential is zero. But in the beaker solution, you're going to be using sodium chloride instead of sucrose, so that has an ionization constant of 2. All the other numbers being the same, what you end up basically doing is making the solute potential twice as negative. So now the water potential is negative 4.86 bars. So it's negative 3.3 bars in the cell, negative 4.86 bars in the beaker solution. And again, water flows from high to low potential. The water's going to be flowing out of the cell. Okay, excuse me. Number 5. It says a plant cell has a solute potential of negative 7.5 bars, and it is at constant volume and immersed in an open beaker solution with the solute potential of negative 4 bars. What's the pressure potential? Well, they gave us a big clue here. It's when they said, sorry about the cicadas. It's when they said the volume is constant. If the volume is constant, that means the cell and the surrounding solution are at equilibrium, and that occurs if their water potentials are the same. So that's the big clue. It lets us set the water potential of the cell equal to the water potential in the beaker. So if we look at this here, again, constant volume, therefore the water potential is equal inside and outside the cell. So the way I represented that, you just say water potential of the cell equals the water potential of the beaker. So they gave us some information, right? They said the water potential in the cell, or not, I'm sorry, the solute potential in the cell is negative 7.5 bars. In the beaker, it's an open beaker, right? So we know the pressure potential is 0. And then they also told us that the solute potential is minus 4 bars. So the water potential of the beaker is minus 4 bars. And we can set that equal to what we know about the cell. The cell is its pressure potential, and then they gave us the solute potential in the cell. It's negative 7.5 bars. If you solve for pressure potential, you find that it's a plus 3.5 bars. Okay? So again, the key to this is setting the water potential of the cell equal to the water potential of the beaker. Alrighty, just a couple more to go here. Let me open up and find what I did for 6. Okay, so in number 6, it says the cell is at 20 degrees Celsius. It has 0.6 molar glucose. Okay, so again, if it's glucose, it's going to have an ionization constant of 1 since it's a carb. It's going to be at equilibrium with its surrounding solution, containing 0.5 molar glucose in an open container. So again, lots of clues there. Open container, you know the pressure potential in the beaker is going to be 0, or the beaker solution will be 0. They're set at equilibrium, so the water potential in the cell is going to, again, be equal to the water potential in the beaker. And all we got to do is solve for the pressure potential in the cell. So again, water potential in the cell, water potential in the beaker are the same because they're at equilibrium. Calculating what we know about the cell, they said it's sucrose, so we know the ionization constant will be 1. It's 0.6 molar, so there's our concentration. 0.0831 is our constant. And then the temperature, again, they gave it to us in Celsius, 20 degrees Celsius. We convert that to Kelvin. So you end up calculating solute potential of negative 14.61 bars for the cell. What do we know about the beaker? Well, the beaker, again, it's an open container, so the pressure potential will be 0. You're still using I think it was sucrose, right? So let me see. So that's still a carb, so ionization constant of 1. They said it's 0.5 molar, so we add that in. And again, it's still going to be at the same temperature, and we still have that same constant. So we find that the overall water potential for the beaker is negative 12.17 bars. So if we set things equal to one another, again, the water potential of the cell being equal to the water potential of the beaker, since they're at equilibrium, we can solve for pressure potential of the cell, and we find that to be 2.44 bars. Okay, so again, the key, just set the water potential of the cell and beaker equal to one another, and then just plug away and find your missing variable. Okay, last thing here, we'll look at number 7. Number 7 is slightly more complicated than the other ones, but it's still no problem for you guys, I'm sure. So what do we know? It's at 20 degrees Celsius. The system's at 20 degrees Celsius. The cell, they give you the pressure potential of 3 bars, and they tell you it's at equilibrium with a surrounding solution of 0.4 molar sucrose in an open beaker. So again, for the beaker solution, it's sucrose, so you know the ionization constant is 1. It's an open beaker, so you know the pressure potential is 0. And we know the temperature is going to be 20 degrees Celsius. So again, they tell us it's at equilibrium, so the water potential of the cell and the water potential of the beaker are going to be equal. With the cell, they give us the pressure potential, and we don't know the water potential because they didn't give us the concentration of the sucrose solution in the cell. Now, if we go to the beaker, it's an open container, so the pressure potential is 0. It's sucrose, so the ionization constant is 1. They tell us it's 0.4 molar, so there's the concentration. We've got our constant. And then again, it's at 20 degrees Celsius, so it's 293 Kelvin. So we end up calculating the water potential of the beaker at negative 9.74 bars. So if we set things equal to one another, we have the water potential of the cell. It's your pressure potential plus your solute potential being equal to the water potential in the beaker. The variable we don't know here in the cell is the concentration of the sucrose solution. So what I just did for the solute potential equation was solve for C. And then if you just continue on and solve for C, you find that the concentration of sucrose is 0.52 molar. The big trick in this, again, set things equal to one another, write out everything you know from the equations, and then solve for the missing variable. If you can do this stuff, you can do anything that they'll show you on the AP exam. More often than not, what they do on the AP exam is they'll give you the water potentials and they'll just ask you to figure out the direction that water is going to flow. So this sort of gives you opportunity to manipulate some of that stuff. And again, if you can handle it, you're in great shape. If you're not there yet, no sweat. In class on Wednesday and Thursday, we're going to practice some more with this stuff and think about ramifications of water potential differences. So good luck. If you have any questions, let me know. Otherwise, we'll see you soon. Thank you.